Today we're going to continue our discussion of rotation matrices. But I want to make one more clarifying remark about forced closure because somebody asked me a question offline. So let's start with that. Okay, so the issue at hand is the following. Okay, so we know that to answer the question of force or form closure, we can reduce the problem to the investigation of an equation of the form AX equals B. Okay, so reduce the problem, okay, to question of existence of solution x, and here x has to be non-negative. Okay, that satisfies some given AX equals B. Satisfying AX equals B, okay, for any given B, okay, so that is for any arbitrary B, okay, there has to exist some non-negative solution X, okay, to this equation. For arbitrary B, okay. Okay. Now here let's take the dimension of x to be n, okay? Let's say A is m by n, so naturally this would mean B is m-dimensional, okay? Okay, so whether it's point contact with friction or frictionless point contact, in most cases planar, spatial, okay, we can always reduce it to a question of this form, okay? Okay, so now we looked at the case when the number of columns is one more than the number of rows. Okay, so if n happens to be n plus 1, okay, so in this case we have AX equals B. And what we now do is we do Gaussian elimination of this equation. So Gaussian elimination. Okay, and we get it to a reduced row echelon form. Okay, the technical term is not important. Looks like this. So there's an identity matrix here, m by m. And then there's one more column. So let's call that column, say, S1. Okay, so let's remind us that it's a column vector. Okay, so this times x is equal to, now B is altered to some other B prime after our row operations. Okay, okay, so here I spent some time convincing you that if S1 here, has all entries negative, okay, then a solution exists. Okay, so if S1, okay, is less than 0, okay, which means that all entries of S1 are negative, okay, then we have forced closure. Okay. Or another way to say it, a non-negative solution x, okay, to this equation exists for any arbitrary b. Okay, So we established that, and I think most people agree with this, don't have too many issues. I guess there's some confusion in the case when n happens to be bigger than n plus 1. Okay, in this case we have, well, let's do it. So we again start with ax equals b. And we again perform Gaussian elimination. Okay, and this time we get reduced row echelon form that looks like this. So now we have more than one column. We may have, say, k columns. Okay, and then, okay, so this times x equals b prime. Okay, okay, so here, what do we do? Now, it's not necessary for all the S1 through Sk to have negative entries. Rather, what we need here is the following. Okay, so if there exists some scalars W1 up to Wk, okay, and these scalars have to be non-negative, okay, such that the linear combination W1 S1 plus dot 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 plus Wk Sk. Okay, so this linear combination of k vectors S1 through Sk, if this is negative, okay, again, negative meaning that all entries of this vector, this linear combination of vectors, is negative, then we have forced closure. Okay, we have forced closure. Okay, so I use this notation. I mean, I call this matrix S. Okay, so another way to say this is we can say that there exists some vector W Rk. W has to be non-negative. Okay, such that. Okay, so this condition, this is just simply S times W is less than 0. Okay, so that's where this came from, and I think there was some confusion about what I meant by this. Okay, so I hope that clarifies things. Okay, good. Now let's go back to the question of how to mathematically describe orientations. Okay. So last time we looked at the rotation group. And we use the letters SO3. Okay, so if you recall, SO3 stands for special orthogonal group in 3 dimensions, in 3-dimensional space. Okay, so the definition was the set of all 3 by 3 real matrices that satisfy 2 conditions. Okay, so among the set of all 3 by 3 real matrices R has to satisfy R transpose R is the identity, first condition. And second condition, the determinant of R should equal +1. Okay. All right, so just from this condition, okay, if we ignore this for now, just from this condition, we know that the determinant of R has to be either +1 or -1. Okay, so we're going to throw away those whose determinant is -1 and consider only those with positive determinant. Okay? Okay, so a couple properties. Well, I mean, it's pretty clear from the definition that the transpose is the inverse, and vice versa. Okay, the second property, if we take two rotation matrices R1 and R2, that is, they both belong to SO3, okay, then their product is also SO3. Okay, so R1 times R2 is also SO3. Okay. Third property. Let's see. If we take a three-dimensional vector x, look at its norm, and then compare that to the norm of r times x, we see that it's the same. Okay, and this is true for all x, three-dimensional. Okay, all right, so what this says is that x and rx are always of the same length. Okay, so rx is some transformed version of x. In fact, it's a rotated version of x. Now, how the rotation occurs, we don't know yet. We'll find out later. Okay. Okay, fourth property. We learned that RAB times RBC equals RAC. Okay, so this is it's pretty easy to remember. Okay, AB times BC, AC. Okay, so what does it mean physically? Well, it means the following. So if we have three reference frames, A, B, and say C, okay, and the unit axes of the A frame, let's label them XA, YA, and ZA. Okay, and similarly for the B frame, we have XB, YB, and ZB. Okay, and similarly for the C frame. The last time I showed you that we can write XB, YB, ZB, okay, in the following form, XA, YA, ZA, okay, times RAB, okay. Let's see, I hope I got the indices right. Okay. So for some matrix, okay, for some SO3 matrix, RAB. Okay. So essentially, RAB is a description of the B frame, okay, as seen from frame A. Okay. Another way to say it, we're describing frame B using frame A coordinates, okay, the orientation. Okay. All right, so what we've established here is that if I want the description of frame C using A frame coordinates, all I have to do is take RAB multiplied to RBC. Okay, so there's a relation here between RAB, RBC, and RAC. Okay. Okay. Fifth property. Okay, so from here, this is new stuff. Okay. Okay, so if I take RAB and then multiply it by RBA, just for the sake of it. Okay. Now we establish that's true. So if we take C to be the same as A, then this is RAA. Okay, so what's RAA? Let's think about it physically. So I'm standing at frame A. I'm going to describe frame A, the coordinate orientation of frame A in A frame coordinates. So what's it going to be? It's the identity, right. Okay, so this is clearly I. So RAB times RBA is I. These are both square matrices. Okay, so what we've just shown is that the inverse of RAB is just simply RBA. Okay, just swap the indices, B and A. Okay. Here's another property. Okay, now this time let me just draw a vector in space. Call it V. Okay, so I have some vector floating in space. Okay, and I want to use coordinates to represent this vector. Okay, so let's say there's a reference frame here. Say, okay, so here's frame A. Okay, so I want to describe this vector in frame A coordinates. What I need to do, I need to sort of slide this vector over, okay, to frame A. Okay, and then okay, so there's my V again, same V, but I've just moved it over here, maintaining the same direction. Okay. So I could do the same thing if there were another reference frame, say here. Let me call this frame B. I can describe the same vector, this time using B frame coordinates by sliding the vector this time to the B frame. Okay, in this fashion. Okay. Now, if I want to represent this vector using the A and B frame coordinates, okay, I can write the following. So V, okay, in terms of the A frame coordinates, is going to be, say, VA1 XA plus VA2 YA plus VA3 ZA. Okay. And I can write this as XA YA ZA, okay, times this column vector VA1, VA2, VA3. Okay, so let me just call that V sub A. Okay, so V sub A, just write it once, is VA1, VA2, VA3. Okay. Okay, I can also write this V in terms of the B frame coordinates as, I'll skip this step, XB, YB, ZB times V sub B for some three-dimensional vector V sub B. Okay. Okay, now what I do is go over here. I see that XB, YB, ZB is equal to this. Okay, so let's take this, substitute it in here. Okay, see what we get. So this is equal to XA, YA, ZA times RAB times VB. Okay. So it follows that this and this have to be the same. Okay, so we get the result that VA is RAB times VB. Okay, and we can also swap notation. VB equals RBA, VA. Okay, all right. So physically, what does this mean? If we have some vector V, okay, we describe the vector in A-frame coordinates, call it V sub A. The same vector V described in B-frame coordinates, call it V sub B. Okay, and V sub A and V sub B are related by these equations. Okay, so the rotation matrix occurs here too. All right. Okay, question? Say it again.
Frame A and frame B
Mm-hmm.
have
Same orientation?
origin,
Same origin? Not necessarily, no. They can be different origin. Okay? But when we say let's write down the vector V in terms of A-frame coordinates, physically what we're doing is we're sliding the vector over to the origin here. Okay? Same thing here. Okay. I think that's enough properties for now. We could go on, but let's stop here. I don't want you to be bored.